Take it away.
All right, thank you so much. Hello there, everybody. My name's Lee Kelvin. I'm a member of the DM team here at Princeton. Lovely to see so many familiar faces in the crowd and online. Wish I could be there in person. Hopefully see you again sometime soon. So I wanted to talk today briefly about the intersection between the science pipelines that we're building to reduce all of this fantastic data and low surface brightness science, because LSST Rubin will be an amazing resource for LSB science. And so it's something that, as we all know in this room, that's very important. So next slide, please. Okay, so I have to start here, this wonderful image of the knife-edge galaxy, NGC 5907. You can see the plane of the disk, and perpendicular to the plane of this wonderful disk, you can see these beautiful low surface brightness stellar streams. I hope it comes out on the view screen in front of you in the room. So this stellar material is a remnant of some past merging activity, giving us an insight into the formation and subsequent evolution of this system. And this is just one example of many different types of LSB morphologies that many of us study and are interested in. For example, stellar halos, LSB galaxies, intracrustal lights, tidal tails, and so on. However, by virtue of, as indicated by their name, these things are inherently very faint. So the kind of benchmark that we all in the literature seem to use is anything that's less than 30 mags per square arc second. Tends to fall into this LSB regime. So kind of getting down to that LSB level is really the holy grail. And as a consequence, because the structure is so faint, it can be very easy to contaminate this structure during, for example, the data reduction process, background subtraction, and so on. Next slide, please. Okay, so here's just an example. It's just kind of one of the nightmare gallery pictures that I have on hand. I've very unfairly picked on CFHT lens, which is a lovely survey. Many wide area surveys exhibit similar features, but here you can see I've pointed out with arrows some of the kind of data reduction ghoulies that can pop out, edge effects, over subtraction, saturation, and so on and so forth. All of these things can leave a tremendous mark on your data. So if you're looking at LSB science, these are the things you want to avoid coming out the end of your data reduction pipeline. Next slide, please. However, good news. So this is one of my older figures, but it's still a lovely one. So I still like to wheel it out every now and then. So this shows the limiting magnitude as a function of wavelength for a number of different surveys. You can see 2-year estimated LSST depth right at the bottom there. So to put that in perspective, the kind of jump in depth moving from Sloan to Hypersur PrimeCam will be again replicated moving from Hypersur PrimeCam to LSST. In the first several years. So really the amazing potential of LSST and Rubin data observations is really quite something. So that's the kind of first bit of good news. Next slide, please. The second bit of good news is that we have an amazing world-class data reduction suite with which to reduce these data that we're going to be taking. So the LSST Science Pipelines is the name of the software. There's more information about that that'll be presented throughout this week. In particular, I highlight the update from Science Pipelines talk tomorrow, being led by Yusra Syed, and others will be speaking as well, which goes into more detail than I'm able to in this short session now on various aspects of this pipeline. And there's also the LSST Algorithms Workshop website, which is from March 2020, so it's a little bit older now. However, many of the principles that were discussed then are still valid today, so I encourage you to check that out if you're looking for more information. Okay, so this is a lovely flow chart that shows kind of some of the key processing steps. So on the left, you can see the raw data going in, your calibration data, and other ancillary data going in. I'm just going to step through some of the tasks that are important to LSB scientists. In particular, I'm going to focus on the background subtraction tasks, because I think of all the tasks that impact LSB science, background subtraction is perhaps one of the most important. So I wanted to take my time today to really focus on that. So the first box that we go into is the instrumental signature removal box, ISR. That's where bias, flat fielding, and things like that take place. And next slide, please. And at the very end of ISR, we have one of our most recent additions, which is the amp-to-amp offset task. I'll talk about that now. However, before I move on, I will just briefly mention there's another session being led by Merlin Fisher-Levine on, I think it's also Wednesday, tomorrow, which focuses exclusively on ISR. So if you're interested in that, make sure you go to that session too. Okay, next slide, please. Okay, so amp offset corrections, also known as pattern continuity corrections, which is the name that that Pan-STARRS gave to this kind of procedure, is the process by which amps are normalized to remove any step delta-like function, delta function-like edges between amps. So on the left here, you can see an HSC detector, and it has these distinctive ramps, which mark out the 4 amps present in HSC data. This is some kind of hardware thing. We've spent a lot of time trying to understand exactly where this comes from, and we're still not entirely sure. However, it is consistent, and we can empirically measure it and correct for it. So on the left is before, and on the right you can see the after image. So this is something we're really quite happy with. So this is switched on now for HSC, and HSC PDR4 will have this switched on by default, and we're looking to implement this in other cameras as well. And if you go to the next slide, please, you can flick between the next 2 slides. If you can do like a back and forth for the room to blink them a little bit. So here I'm showing again the same detector on the left-hand side, but you can see on the right-hand side the full focal plane, which shows this really works across the whole focal plane. These kind of signatures are kind of everywhere with HSC data, and being able to correct for them really assists us in accessing the LSB regime. Okay, next slide, please. Okay, so once we come out of ISR, we're into characterize image task and calibrate task. This does a whole bunch of PSF estimation, WCS, deep blending, source detection, and so on. However, in terms of background, there's also a very initial naive background model which is estimated. Next slide, please. So the post-ISR CCD comes out. This image is binned up. Detected sources are masked, and then a 6th-order Chebyshev polynomial is fit to the remaining pixels to generate a background map. This is a process that will be familiar to many people in the room, I'm sure. And the background model is subtracted from that image to produce what's known as a PVI, a processed visit image, and you may hear us refer to that as a CalExp, a calibrated exposure. PVI is the official name. So that's the kind of end of the line for single frame imaging for your source catalogs. So if you're looking at source level imaging, that's the data that you'll have access to. However, next slide, please. However, if you're going on to co-addition, which obviously in the LSB regime is where it's all at, you want the full depth of those co-added images, then actually that initial naive background model isn't used. What is used instead, and here I'm referring to HSC in particular, and again this is something we're looking to roll out to other cameras going forward, is a full focal plane sky frame is constructed. So next slide, please. Okay, so this is a figure from Ehara et al. 2019. So here's an example of the 6 different sky frames for HSC. This is what they look like. So these are temporary coherent spatial structure, that structure that doesn't change in focal plane coordinates. So this structure is kind of larger than a detector, if you will. It spans the whole focal plane. So these sky frames are constructed in advance in a kind of calibration data set sense. And then variations of these data are scaled and subtracted off the original detectors to produce a more robust background model for co-addition. So that's a kind of very important step to consider in the background process. Next slide, please. That has a huge impact. This was switched on for PDR2 of Hypersuprime Cam, and you can see the impact it has here. This lovely figure, again from the same study, which gets rid of this so-called divot over subtraction around this extended galaxy here. So it's very nice. It produces very nice results. Next slide, please. Okay, so there are two more steps that I'm not going to go into details in this session now. So there's at the coad level, there's an aggressive spline coad background subtraction step that takes place, and then there's a dynamic detection step that takes place. Next slide, please. So the reason I'm not going into those details is because those data that are produced as an output of those two background steps are probably not appropriate for LSB science, and this is why. So on the left side here, you can see what's referred to as the deep coad dataset type. And on the right-hand side, you can see the deep coad CalExp dataset type. So the left is the coad pre that final aggressive background subtraction, and on the right-hand side is that coad post that aggressive background subtraction. Now, for LSB science, you probably don't want to be using the image on the right. I think that's fairly obvious from looking at this image why that's the case. So for LSB science, if you're accessing data that comes out of the science pipelines, the dataset type you should be requesting is probably the deep coad and not the deep coad CalExp. Okay, next slide, please. Okay, so I just have a few more slides on kind of other things that we're looking at, future prospects, and other things like that. So background subtraction is all well and good, but we want to also stress test everything we're doing. And one of the ways another thrust that we're approaching on ascertaining how well a job we're doing at that is looking at source injection. So we're in the midst right now of setting up a new source injection repo on GitHub. Anyone can have a look at that and please let us know your thoughts. And we'll be injecting synthetic sources into our imaging and then using those processed outputs to ascertain how well a job we've done at background subtraction, as well as other fidelity metrics on those sources. I won't say too much more about that now, just to say that there is a session on Thursday being led by Sophie Reed on source injection in the Rubin pipelines. So I do encourage anyone with interest in that to attend that session on Thursday. Next slide, please. Okay, something else we're looking at is bright star subtraction. So this is something we've been looking at, we've been prototyping for a while now. It was work initially kicked off by Morgan Schmitz prior to him leaving the project last year. But a lot of effort was made, and we're looking to kind of wrap that up now. So the genesis of this really is quite simple. So we take bright stars, you model them, you construct a bright star model, and then you subtract them off. And if you blink this slide and the next slide, you can kind of see a very this is an an older image now. If you can just blink between those, showing kind of the impact of that on this example HSC G-band data. So there is more work to be done, but the ability to remove not necessarily the cores of these structures accurately, but the wings, the halos of these bright sources, and the improvement that has on being able to estimate flux and other properties from the sources that lie in the wings of those bright sources is extremely important and has a huge impact again on LSB science. Next slide, please. One more. There we go. Thank you. Okay, so we're also always trying to consider new novel techniques. Here's something that I've been looking at recently with Tony Tyson, Imran Hassan, and others. Looking at trying to improve further the background that we subtract off. Here is an approach called modeled masking that we're advocating, which is essentially fitting bright extended sources with Sersic functions, parametric functions, subtracting them off, and then using that residual map to construct a more accurate background map. During the testing on this in our paper that's been submitted, the results are very promising. The background is of the order of 1 mag per square arc second fainter than just doing a naive background modeling technique. So this is kind of similar to the bright star subtraction approach that you saw earlier, but it's for extended sources.
Lee, okay. 1 minute.
Thank you. Next slide, please. So my summary slide. So Rubin is ideal for LSB science, and many of the data outputs that are coming out of the science pipeline should hopefully be LSB ready. But we're always keen to interact with the community, with people in this room and people on this call, to develop new techniques and new metrics and plots that can tell us how good a job we're doing, for example. So we love having those conversations. Please do get in touch. as we've discussed, a number of different background algorithms that operate throughout the stack, and I think those are all important to have in mind how your data is being reduced when you're looking at LSB data science with Rubin. I mentioned that the deep coad dataset type is probably the one you should favor over the deep coad calyx. That's a really important point to take home, because you may be using one and wondering why your LSB results don't look as they should. And as I mentioned, we're continuously trying to ascertain how good a job we're doing with things like source injection, looking at developing new plots and metrics, and validating everything we're doing. And as I said, we're always looking for new novel techniques to implement in the stack as well. So I think that's all I have to say. Please do get in touch, ask questions, happy to answer and talk at any time. And thank you for listening.
But that was a good clap, Lee. So questions, we've got a few minutes for questions. Do we have any? I'll go Michael, because he's very enthusiastic, and then Sagata, I'll check if there are any online.
So Lee, can you go back to the first picture that was labeled calyx?
Yeah, I don't have control of the slides, but I'll let whoever's got that.
Yes, wait, okay, further back, before the coating. Yeah, that one. So the calyx exposure, I still see structure in the background, sort of, especially in the lower half of that image. This is after the calyx background has been subtracted. Is that physically real? Can you comment on that at all?
That's a great question, and I guess it leans into one scientist's trash is another's treasure. So there are different concepts of what constitutes background. So, for example, is cirrus the background? If you're interested in cirrus, probably not. So some of these structures are undoubtedly real. I'm not familiar. I have to go away and look at a broader cutout of this particular detector to answer your question properly. But looking at it now by eye, it probably could be real structure. Yeah, absolutely.
Let me just check if there are any online. Nope. Aaron. Okay, if that one's you can grab the one to your excellent.
So let's see. On the camera side, as we're finishing up our verification testing, we've explored a lot, a handful of particular behavior of our sensors, especially in the overscan or biases, and we've seen plenty of kind of 1 or 2 count anomalous behavior that we're working, continuing to work on to understand. For low surface brightness science, it would be very useful on our side to have a guideline at what level, are things good enough. You showed correcting things at a count, so maybe a count is still an issue. But is a tenth of it, if the overscan and bias look clean to a tenth of a count, is that good enough? What would you say if you had to pick one number? What would it be? If you can do that.
To put me on this, I'm not sure I could give you one number right now, but this 30th mag per square arc second boundary is the real gold standard for entering the LSB regime. Now, I'm not sure who's in the room exactly, but I'm aware that people in DESC have been discussing this issue at length recently. And coming up with a number is actually something we should focus on. So I don't have a number for you now, but I know those conversations have been ongoing, and I'd be more than happy to join that conversation and talk about that going forward.
Thank you, Lee. We'll bring the questions to a close there. I know I'm going to ask one on Slack in a moment, and there's another question from Tom on there. Yusra answered Michael's question saying that CCD was chosen for the to have the cirrus. Yeah. Yeah. Okay, now let's go. We've got Lee Aaron talking next, but I will set this up. Just kidding. It is. How do we do presenter? Oh.
Check the dots on the right.
Thank you.
The other one.
So, those ones.
Okay, never mind.
No. That one.
Oh, this icon here, extras.
You're okay with that? And I'll bring
I
you
can
the.
see that.
Yeah. I'll give you 2 minutes notice.
Okay. Okay. Yeah, so following up on Lee's talk, I'm going to be discussing some work that we've been doing looking into the LSST pipeline sky-subtraction, just how well it seems to be performing for LSB science. We've been looking into a number of potential alternatives that might do a little bit better. So I'm just going to scroll down because the page down thing isn't working. So just to motivate this a little bit more, as I'm sure we're all aware as LSB people, the theoretical 10-year depth in surface brightness for LSST is something like 30 magnitudes per square arc second in G and R, and close to that in the other bands. So, feedback. So if we get even close to that, maybe won't get it perfectly, but if we get close to that, then LSST will be the first survey to really produce statistically robust samples of things like dwarf galaxies, intercluster light, tidal streams, and lots of other things. So that means that the LSB regime imposes a very large fraction of LSST's potential discovery space. So obviously, as Lee already mentioned, this all hinges on making sure that the LSB flux is preserved in the images. If it's not, we can't obviously do any of this stuff. So to that end, last year, we were working with DM to inject something like 1,000 or so models of galaxies into the pipeline just prior to the full focal plane sky subtraction, which Lee just mentioned. And we just did photometry on them after the fact on the coads, the deep coads that are good for LSB science, just to see what happens to them. And the results are summarized in the plot on the right here. This is showing isophotal surface brightness, the average isophotal surface brightness in these models. And the y-axis is the amount of flux that was over-subtracted at that isophote in units of surface brightness. So I guess the axes are a little not like this microphone. But let me use the handheld. I'll switch real quick here. Okay, let's try this one. The point is that at around 26 magnitudes per square arc second in the average model, we were seeing something like 1/10 of a magnitude per square arc second over subtraction and flux. By 28, it's about 0.5, and by 29, we were seeing multiple magnitudes over subtraction. So I'm showing a visual example of this on the lower right, which is an image of one of the models that we injected on the coad. So this is post-sky subtraction. And you can see that in the very outskirts at very low surface brightness, you still see these dark rings that were present in the earlier sky subtraction. It's obviously much mitigated, but it's not completely gone. So given that, this seems to be affecting things that are large and diffuse the most. So stuff like ICL is getting pretty shredded by this, but it was affecting basically everything that we injected to some extent. So we started thinking about potential alternative algorithms that might solve this problem. And at the moment, we've come up with 3, 2 of which are somewhat simple, the third of which is highly experimental. That's what I'll be talking about for the rest of this. The first potentially simple fix is very easy to implement, I should think, and it basically involves simply masking the flux to deeper levels than is currently being done, and then using a low-order polynomial fit to the unmasked pixels. So I've done some experiments on this using synthetic images. I would just populate these images with fake stars and galaxies and then add whatever kind of sky I wanted on top of that and see if I can get that sky back. The bottom panels are showing what happens if you have a flat sky in your image and then you purposely overfit that sky with a 10th order polynomial. The image on the right is the fake image I was using. The 4 images on the left are the residuals of a sky subtraction for different mask depths. So down to 22 mags per square arc second on the left, and then masking down to 34 mags per square arc second on the right. You can see that if you have a shallow mask and you use a 10th order fit on a flat sky, you get these strong over-subtraction divots around bright extended objects like galaxies. The plot on the upper right is showing the same thing, just quantified for a variety of different polynomial ordered fits. It goes from first all the way through 10th, from the purple all the way to the yellow. And this is showing amplitude of the residuals, so just the maximum minus the minimum of these residual sky subtracted images as a function of depth in the masking in surface brightness. And so if you look at these dark curves on the bottom, those are the first and second order fits. You can see that you can get away with a lot shallower masks and still get back basically the same sky you put in without worrying about accidentally over subtracting your sky. Now, of course, the big caveat here is that you need to have pixels to fit in order to model the sky. So if you have a really crowded field, or if you have like a large nearby galaxy that takes up most of your frame, you mask that down to 30 mags per square arc second, you don't have any pixels left and you can't fit your sky. So this isn't a 100% solution, but it could be a very simple way to get 90% of the way there. Another alternative is something I learned from the folks who work on Elixir LSB, if anybody are familiar with that. That's what they use for CFHT imaging. I think they're thinking about using it in Euclid as well. And the basic idea, it's akin to the chop and nod strategy in near infrared, where you take a bunch of dithered exposures, which were taken close together in the sky and close together in time, close enough together in both of those things such that the sky doesn't appreciably change. You then just combine all of those together and you do some Gaussian smoothing to remove some of the small scale fluctuations that are left behind. The plots that I'm showing on the right, on the upper right, is just showing how this converges as a function of the number of frames exposed, or the number of frames combined. And you can see that, again, after about 10 to 12, you start to flatten out. But a couple caveats here. If you can see the label there, it doesn't flatten out to 0, which would be I'm getting back the sky that I put in. It flattens out to a positive number. And this is coming from low surface brightness flux that is just sort of residual on every single frame from things like extended point spread functions or the wings of galaxies. So you always get this sort of pedestal level. Now that's not critical flaw. You can always try to estimate what that value is and then take it back out. But this does rely very heavily on the dither pattern and the cadence of your survey. So if you don't have 8 to 10 exposures that are taken while the sky is not changing, then this isn't going to work because you'll be subtracting the wrong sky from every frame. The other issue is noise. Because you're just combining exposures together, just median combining them or whatever you like to do, you can beat down the noise by smoothing, but you can never completely get rid of it. So the lower right panel is showing the standard deviation, the difference in the standard deviation of the model sky versus the input as a function of number of frames combined. And you can see it has this sort of 1 over square root n type behavior. So you can approach 0, but you can never get there, which means this will be adding noise when you subtract your sky from every frame. But the nice thing about this is that it's model independent. So those are 2 options that we might consider looking into. The other is a very novel method, which I believe Yusra and Robert came up with back in the SDSS days, if that's right. And the idea here, as I understand it, is the problem with modeling the sky, of course, is you have all this LSB flux in the way, getting in the way of your model. So if there's a way to remove that, then you're much better off. And the idea here is to first produce a preliminary sky subtracted coad using whatever favorite sky subtraction method there is. Then you take that coad, you align it with an individual exposure, you scale it in flux, maybe you PSF match, and you subtract it off. So as long as you don't have strong residuals in your coad backgrounds, this will remove all of the stars and galaxies and basically anything persistent between the coad and the individual exposure from the image, leaving behind just a map of the night sky in that particular frame, plus a lot of other stuff, cosmic ray hits and things that don't subtract off. Okay. You can then take that image, you can further process it to reduce noise and get rid of artifacts and use it as a model-free map of the night sky tailored to an individual exposure. So we thought this was a very interesting and cool idea, so I've been looking into this as well. And naturally, I've run into a couple caveats here too. So the first one is the noise reduction issue. When you take a coad, which has its own noise characteristics, and you subtract it from an individual frame, which has its own noise characteristics, you get an extremely noisy map of the night sky. So you have to do something to bump down that noise if you want to use it as your sky model. You can fit it using a function if you want, but if you want a model-free thing, then you have to use some kind of a noise reduction software. And there's 100 of these available, but the one that I think is the most scalable to LSST, the fastest one, would be your standard binning and Gaussian smoothing, which again runs into the problem of the coad sky that I mentioned before that Elixir LSB uses, where you're never going to get rid of all of the noise. I'm showing an example of residuals from this coad subtraction technique on some simulated images on the right. And you can see that you end up with this sort of Gaussian pattern at the binning/smoothing scale that you use to get rid of your noise. So again, you'll be adding a little bit of noise onto every frame that you subtract these from. The other issue I ran into, which is maybe more critical, which I'm still thinking about, is that I often find you get very minimal improvement over your initial sky subtraction by doing this. This is kind of a philosophical thing, but if your first coad with your sky subtracted isn't already very good, in other words, if it doesn't have a lot of large-scale artifacts and residuals from your first poor sky subtraction round on it, that's what you want, right? You don't want to be imprinting large-scale artifacts onto every frame when you subtract your coad. So it has to be very good in the first place, but if it's already very good, then the second time you go back and estimate the sky again and then redo the sky subtraction using this technique, you get very small improvement over the first round. Usually, I was measuring this in terms of limiting surface brightness, and usually I only could get improvements of maybe 1 to 5%. So the big question here is, if that's the case, does that justify the added processing time needed to make a second coad and then go back and re-estimate all your skies? And then at the moment, I'm not completely convinced that it does. However, I have been thinking about this. I think a potential fix here is what I've been doing for this technique is to use the entire image set that I have to produce the first coad. But this is LSST, we'll have tons and tons of images. You don't have to do that. What you could do instead is take, say, your top 20 to 30% of exposures for that part of the sky, defined in some vague way. I'm not sure how yet. Maybe those taken at low air mass under dark conditions with good seeing. And then you use just those frames to make your first coad. And then you go back and you correct only the frames taken in the worst conditions, which would be things like strong moonlight, maybe taken near a bright planet, or near the horizon where there's a lot of city glow and stuff like that. The reason I was thinking of this is because LSB observers, our usual strategy is if you have bad frames in your stack, you just throw them out. That actually improves your limiting surface brightness a lot better than keeping them in. But in this way, if you go back and instead fix them, you can improve your limiting surface brightness while maintaining the point source depth in the LSB-friendly coad. So assuming that this works, it's kind of an everybody wins type situation. So that's where I'm at on my thinking right now. So I think I'll just leave up my summary and take your guys' questions for the time being. Of course, we'll have time at the end of the session too, if you can think of something right now.
So, what if you want to work galaxies with
Yeah, okay. I don't know if your mic's on, so I'll repeat that. But the question was, in order to do that second strategy, you need to dither the exposures so you avoid, having the flux in the same place in the same time. And doesn't that ruin the second method? I think the second method relies on the sky being stable across the dither pattern, which, if you do it right, it tends to be. I know they have used it successfully in CFHT imaging, mainly to remove optical effects, but the skies in those are pretty insensitive to it as well. And they have been using this technique in some form in near-infrared imaging for a very long time. Granted, they do a much different kind of observing strategy where they just take incredibly short exposures and just sort of hop back and forth. So I don't know exactly if it would work in LSST. Again, it depends on the dither pattern and the cadence, I think. So but I think it's worth exploring, I guess is the point. I guess we're out of time.
We're out of time, so we'll keep remaining questions for the discussion at the end. So I'm going to ask Gareth to...
Okay. That.
Yeah.
Oh. Can we just open it in the normal PDF reader, maybe?
Yes.
If you click the
There you go.
ah amazing. Okay. Oh, there is a clicker. It doesn't work though. Okay, thank you. Okay, yeah, so hi everyone. So today I want to talk about some work that I've been doing in collaboration with the LSST Galaxies LSB working group. So just to begin, I'll give some very brief background, but I'm sure we'll kind of get the picture. So we obviously know already, assuming everything goes to plan, the kind of quality of imaging that we are going to get from LSST, right? And from Rubin. So, for example, we have the Subaru hyperprime cam survey. We have various smaller surveys which show us that we can achieve something like a 30.5 magnitude per square arc second limiting surface brightness. And so you can see here the kind of improvement over something like SDSS that we can get for this in terms of resolving the outer halos of galaxies at low surface brightness. And so, the primary advantage with Rubin Observatory is the sample size, right? So we have the entire southern sky, hopefully, where we can get these kind of quality of imaging. And that means that we can start to make, statistical comparisons to the kind of lambda CDM predictions that we expect from theory. And so we can start to make predictions for the frequency and distribution of the features that we'll see in the stellar halos of galaxies. And it's also important, to understand what the detectability of these features in terms of limiting surface brightness, their morphology, etc., we would expect, and what biases also we can expect from things like the orientation of the galaxy and with redshift and limiting surface brightness, etc. So to that end, we're making use of the New Horizon simulation. So this is a cosmological kind of intermediate volume simulation. So it's we're not covering the entire range of environments that actually exist in the universe. So it's 16 megaparsecs all cube volume, but we have extremely high spatial and stellar mass resolution, which means we can actually resolve down to very low surface brightnesses the content of the stellar halos of these galaxies. So we can start to resolve Milky Way mass galaxies and below, basically out to their stellar halos. And so here we have taken basically a sample of about 150 objects from the simulation, from kind of intermediate to Milky Way kind of masses. So our procedure here is to first decompose these simulated galaxy stellar halos into a couple of components. So here we see is there a laser? Yep. So here we see the surface brightness map of a galaxy. And here we can see the dense total substructure. So basically I've taken here a density cut that maximizes the high spatial frequency component of the object. And then the remaining part we have is the diffuse light. So this is the low spatial frequency component of the stellar halo. And this is after removing the actual galaxies from the particle distribution. So with that, we can start to look at the flux distribution within the stellar halo. So if we assume we can achieve a surface brightness limit of something like 30.5, 30.3, then we find that this is sufficient actually to recover about half of the flux within the dense component of the stellar halo. So these essentially the tidal features. For the much more diffuse light, we see that this is going to be essentially, without any kind of binning or any other processing, essentially inaccessible to LSST, realistically achievable surface brightness limits. But this is a component of the stellar halo that accounts for about a quarter of the total light. So most of it is in kind of Milky Way mass galaxies and below, not in more massive galaxies or clusters, is within these dense tidal features. So here I'm showing you the fraction of detected flux within these tidal features as a function of the limiting surface brightness of the survey. And so in the nearby universe, for galaxies less massive than 10 to the 10 solar masses, so this is basically this blue line here, they're unlikely to host any kind of detectable tidal features that Rubin will be able to access, and that's at the 10-year depth of the observatory. But for a majority of the more massive galaxies, so red we have 10 to the 11 to 10 to the 11.5, yellow 10 to the 10.5 to 10 to the 11. A majority of these objects will host detectable tidal features at a 10-year depth. So about 80% of Milky Way mass galaxies with this 30.5 magnitude per square arc second cut. If we take a more conservative cut of 29.5, then we can expect to see about 60% of these objects with tidal features. And of course, this is going to fall as we go to higher redshift. So, if we go to a redshift of 2 with this 30.5 magnitude per square arc second flux, then this is going to fall to about 10% of flux within, 10% of these Milky Way mass galaxies are going to have detectable tidal features. The kind of second exercise we did here was to produce Rubin-like mock images. And so you can see here that the simulation produces a range of tidal features that we expect to see in reality. And we asked a group of 50 expert classifiers to actually look at these images and try and characterize and count the tidal features that they see within these synthetic images. So we're interested here in the effect of various biases. So how does limiting surface brightness affect our ability to detect these features? How does redshift, and how does the orientation of the object, so what projection we see the object in, how does that affect our ability to see these tidal features? Does that work? I don't know. No, it's a PDF. Am I going to be able to get internet to show a video? Let's see. Let's not bother. Okay, so as I said, there are various sources of uncertainty here. So the surface brightness limit, the surface brightness dimming that we get with redshift, orientation of the object, the PSF, the chance projection of other objects, ambiguity, the general ambiguity that you'll get between people classifying objects. And so when we look at how different classifiers classify the same objects in different orientations, so this is a plot where I'm showing basically the level of disagreement between classifiers on the y-axis, where we've controlled for the projection, and on the x-axis where we've controlled for so we're basically looking at the average scatter among different classifiers for the exact same image, right? So this is how well classifiers agree on the same images, and this is how, if we average over the actual different orientations, what we get. And so you can see, so the color coding here shows different limiting surface brightnesses, but as we go to higher fainter limiting surface brightnesses, the disagreement generally improves quite a lot. And so if we look at the circle one, so this is for all types of features, you can see you generally get an improvement with limiting surface brightness. However, for some categories of tidal feature, and specifically here, kind of merger type tidal features, then we see that actually the classifiers start to disagree with each other a lot more as they go to higher limiting surface brightness. Right. So, thank you. So essentially, what we're seeing is that generally there is at any realistic limiting surface brightness that we could achieve with LSST, there's going to be quite a significant level of disagreement in terms of the characterization of these features. And also, basically as the images are becoming more busy because we're going to fainter limiting surface brightnesses, this can also actually start to make our ability to discern different features within these images more difficult. I'm just going to go to the last slide because I don't like to talk about it. So at the end of the 10-year survey, Rubin should have sufficient depth to resolve quite a significant fraction of the flux that we find in the tidal substructure of Milky Way mass galaxies and more massive objects as well. About 75% of the flux within these Milky Way mass stellar halos actually lies within these denser tidal substructures rather than more diffuse kind of tidal debris. If we go to sufficient depth, so in this case, if we were able to get to something like 35 mags per square arc second, then the majority, by basically 100% of these objects would have tidal features that we could see. Obviously, we can't achieve this. And if we look at the kind of concurrence and the ability of human classifiers to actually characterize the tidal features that they will see in these images, this will generally improve as we go to fainter limiting surface brightnesses. But as the kind of morphologies of the tidal features within these images becomes more complex, this can actually introduce quite a lot of uncertainty into the kind of precise characterization of the tidal features. With that, I will take any questions.
Okay, thank you. Nice talk. I had a question for what you had at the beginning about decomposing the galaxies into this one.
Yes.
So what you actually do is that you said that you subtract the galaxy and then the rest is somehow divided into dense and...
Yes, so there's initial step. So we use a structure finder to remove the galaxies.
Use what to?
We use this. So in the simulation, we use a structure finder to remove the actual galaxies. So there's some...
So that's like a particles that are bound or something like that. Yes. In phase space. So you think that you actually do like analyze the upper part of the galaxy and you just divided it into dense and...
Yes.
And do you think that by this, like removing the bound particles, that you can actually remove also a lot of tidal structures as well?
No, I don't think there are many tidal. So essentially, like very bright tidal structures, like very close into the galaxy, will probably be removed, but the majority of the tidal structure that's much fainter is not captured by the structure finder, and it shouldn't be. They should be kinematically distinct anyway from the galaxy.
Okay, thank you. Thank you. Nushka, you're up next. I'm just trying to get you present.
Can everyone hear me? Just to make sure that works. Yeah, okay, awesome.
Yes. You're a little bit quiet, so...
Oh, okay, sorry, no. It's just really late. Yeah, sorry.
That's better. Thank you. I'd say go, and I will keep working on this. Give me a moment.
Okay. Yeah, so hi everyone. I'm Nushkia. I'm a postdoc at Stockholm University, and I'm going to talk to you about the work I've been doing on the edges of galaxies. Next slide, please. Okay, no, okay. I guess some text might be cut off, so I apologize for that. But in this slide, I'm showing you galaxies from the Stripe 82 legacy project. This data has a limiting depth of 29.1 magnitudes per arcsecond squared in the metric I've put on the screen. And the point here is that, so I've shown you galaxies that are scaled to the same distance, and these are all images from the same survey. And what I've put on circles of different colors in all of the images is where the effective radius is. And this effective radius, it's one of the most popular galaxy size measurements for galaxies for their size. And the point here I want to make is that when you see that most of the in radius for these galaxies, the size is close to the centers, and the reason is because the effective radius, it traces the concentration of galaxy light, and this is because it's defined where half the light is. And so for the most massive galaxies, it's mostly in the center, but this might not be the case for the smaller galaxies. Next slide, please. And so what we did, and this has work from my doctoral thesis in 2020, we tried to redefine galaxy size because the effective radius doesn't capture the visual extensions because it traces the concentration. And so we developed a new physically motivated definition, which is based on a gas density threshold for star formation. And in 2020, what we did was we explored a fixed threshold, and that was a proxy for this definition. I put all the references for you to have a look if you're more interested in this idea. And now today what I'm going to talk to you about is what we've done to expand this definition. And we actually looked for a signature for the edge of star formation. And we did that by looking at where there's a sudden drop in situ star formation, either past or ongoing in galaxies. Next slide, please. So a proxy for this edge of star formation, we used the truncations of disk galaxies. This has been discovered before in the 70s. And essentially, these plots here are radial surface brightness profiles of galaxies. And all of a sudden, as you can see at the outer part of the galaxy, there's a cutoff in their profile. And there's a lot of work that has been done before to understand what this could be in terms of the structure of the disk. And one argument is that these truncations are related to star formation thresholds. So we use this as a proxy for our definition of the edge. Next slide, please. And so what we did was to look at where the edges of 1,000 galaxies are. We looked at dwarf galaxies as well as giant galaxies, so spirals and ellipticals. And we did that by looking at their radial profiles. So we looked at their surface brightness profiles, color, and stellar mass density. And we used the location of their edges, which we call our edge, as the measure of galaxy size. And then we studied their scaling relation. So this work has been resubmitted, so it should be out hopefully by this year. Next slide, please. The data that we use, so very quickly, we use the GNR band images of the Stripe 82 survey, which I introduced earlier. And we have galaxies from the Nair and Ibrahim 2010 catalog, and also dwarf galaxies from the Portsmouth catalog. And what we did was to measure the location of the edges, the stellar mass density at the edge, the color, as well as their stellar masses of the galaxies from the radial profiles. Next slide, please. So this is a visualization of some of the galaxies in our sample. What I've shown here are late type galaxies of fixed mass, and I've ordered them according to their orientation. So from top to bottom are edge on and going towards face on. And this is to show you how their profiles look like for different orientations. So in the second panel are the surface brightness profiles, in the middle are the color profiles, and in the last panels are the mass density profiles. And in the surface brightness, I'm showing the optical GNR and also data from Galax. Okay, so this is NUV and FUV data. And what you see in the dashed vertical lines are the locations of the edge that we've marked out for these galaxies. And you immediately see that if you have lower inclination galaxies, the edges are more difficult to detect. But with the help of Galax, you actually see that you can still see where the truncation is. So this is just to show you how we detected the edges for these galaxies. Next slide, please. And so these are just to show you quickly the results. So this is the scaling relation. On the left is the location of the edge as a function of mass, and on the right is the mass density at the location of the edge as a function of mass. And I've put also the best fit lines for these scaling relations. The dashed lines in the left plot are showing you lines of constant mass density within the size of the galaxy. And what you see here is that there is a dependence of the stellar mass density as a function of mass, and we do find a tilt occurring at around 10.5 log mass in log units in the mass density of these galaxies. Next slide, please. In morphology, this is where the dwarfs and the ellipticals and spirals lie. You basically see here that the galaxies pretty much line up on the same relationship on average in size and mass. And then you see that most of the galaxies that are causing the tilt in the mass density mass plot are the massive elliptical galaxies. Next slide, please. I mentioned that we also looked at the colors of the galaxies, and so these here are the colors at the edges. And what we found was that there was a gradient at a fixed mass, especially if you look at the regime between 10 to the 10 and 10 to the 11 solar masses. We found a gradient where the color of the galaxy changes at larger sizes. So essentially, we found that bluer galaxies have larger sizes, and you see that gradient both in the size mass as well as the mass density mass planes. Next slide, please. So a closer look, this is a summary of what I told you. So basically we found that the edges, they appear at varying stellar masses, stellar mass surface density, and it is a function of both stellar mass and morphology. For the spiral galaxies, the edges appear on average at 1 solar masses per parsec squared. For the dwarfs, it's about half of that. And for the ellipticals, it can be 3 or even higher. We found that bluer galaxies are larger for late-type galaxies, especially, and that there's a global slope in the RH stellar mass plane with a slope of 1/3, and this has a low intrinsic scatter. This is less than 0.06 dex. To give you an idea, compared to the effective radius, this is about 3 times smaller. So these results will be coming out soon, hopefully this year, so stay tuned. And next slide, please. Just because I know that this is going to be a discussion, so I just want to tell you a little bit about the best data now, one of the best data we have to also test these ideas. This is from the LIGHT survey. It is LSST-like in terms of resolution and depth. And so this idea has also been tested using this data. So this is a visualization of the depth of this data. You can have a look at this paper. Next slide, please. And so this is NGC 1042, the galaxy. And so in this paper, we looked at how this LBT, so the Large Binocular Telescope data, compares with previous surveys. So it's about 5 magnitudes deeper than the SDSS. And this is showing their surface brightness and mass density and color profiles on the right. And this is to show you that it is possible to also detect the edges here. And with Rubin, we could detect these edges as well. And it will be significantly better than the past surveys.
Nishka, 2 minutes to go.
Yeah, okay, and I'm on my last slide. Next slide, please, if you can. Yeah, so my main take-home messages are that deep imaging has allowed us to look at size from a different view and to look at it from a physically meaningful way and reach the edges of galaxies in terms of their star formation. And we have now measured the edges of 1,000 galaxies and found that the edges appear at varying stellar mass surface densities, and it is a function of mass and morphology. Thank you.
Thank you. Any questions for Nushkia? Okay, while people are thinking, I have one. So I was curious how you measure this size for elliptical galaxies where you might not have a gas measurement. That wasn't totally clear to me.
Yeah, so we're not necessarily looking for ongoing star formation. So you can have the star formation, you need to think about it for elliptical galaxies as past. So it doesn't need to be ongoing. So I don't have the backup slides in the slides that you have. And actually, I don't realize I don't even have it on my laptop right now. But we did find similar truncation features in the elliptical galaxy profiles. And what we found was that in their color profiles, there is a significant drop into bluer colors in the outskirts. And so we interpreted that as a way of measuring their edge in the sense that there could have been a more recent infalling bluer material into the galaxy. And then you have most of the bulk or past star formation that are in the core part of the galaxy. So the measurement doesn't depend on whether the star formation is happening now or in the past, if that makes sense.
Found like lots of blue elliptical galaxy halos. Which is
it's bluer compared to the core, right?
No, sorry, as in you found lots of halos to go and study, I think was my thought process.
Oh, right, okay.
Yep. Michael.
A very interesting talk. I wonder if you can say a little bit more about whether tidal features confuse the search for these edges. If the galaxy isn't completely quiescent dynamically, is that going to affect your ability to define where the edge is?
That's a great question. Thank you. So for this particular work that I showed you with the Stripe 82 galaxies, we particularly chose galaxies that were not disturbed. And so the sample is very similar to what we used in the 2020 analysis, where we've used a fixed threshold. And even in that paper, we made sure to select quiet galaxies, because of course you don't want your radio profiles to be contaminated by disturbances or asymmetries or distortions. So we tried our best to not have contamination from those issues, at least in this analysis.
Yeah. Okay. Thank you, Nushkia, for that. That's great. I'm going to stop sharing to allow for the discussion part of this session. Might be easier than said than done. Okay, I say that. Stop sharing. Okay, so you can see the room, you can see me. So we didn't pre-prepare any specific questions. I probably have some thoughts, but would like to open the floor and obviously Slack as well for low surface brightness questions that you have, either raised by these talks or just in general with Rubin. That might open a Pandora's box. Any questions? Michael? Yeah.
So this is actually a question for Lee. One of the things that Lee, that if Lee is still on remotely, yeah.
Yes.
You showed at one point the full HSC focal plane, and we're showing. I think there was a specific image in which you were showing that the AMP problems were and boundaries were well taken care of, but there was all kinds of other interesting structure in that plot, and I don't remember at what stage that image was and how much of that additional structure was taken out.
I'll see if I can actually bring that picture
Okay.
back up.
Which
might take a while.
do you remember which one it was? It was sort of a third of the way through his talk.
Yeah.
The question is, when one looks at sort of those wide angle images, it still looks quite frightening for looking for really low surface brightness things.
Yeah, so that's a great point to flag up. So the image you're looking at there on slide 8, 9, thereabouts, as soon as that comes up, does have a whole bunch of other issues on it. So this is the end of single frame processing, but you'll recall I mentioned that the visit level backgrounds that are generated aren't used to generate the coads. So there's a full focal plane background that's constructed. So that will take care of hopefully some of these issues. And then in
for the full frame, keep on going.
Slide 8 or 9, I think.
Yeah, that's it. 8. Go to 9. Yes.
9 is the after.
Yeah, I'm talking about the right hand plot there. Yeah, so that's a degree or so across, and there's all kinds of interesting things going on there. Yeah.
There is indeed, yeah. So I guess there's a few things I'll mention. So first of all, I guess the obvious one is that I have scaled this image on purpose to kind of bring out background fluctuations. So it's probably, you can play with the scaling, and it's probably not as bad as I've made out to be. The second thing is, if you check out AHARA 2022, I'm sure you're familiar with it. There have been some improvements made as well to some of these whiskers and so on and so forth in how they're handled. In PDR3 onwards, so there have been some improvements made there as well. But yeah, and as I said at the beginning, so some of these effects you're seeing here don't make it through to the coad because there is a full focal plane background that's generated thereafter. So this is the kind of end of, if you're only interested in visit level, source level data, then this is what you're working with. And sadly, a lot of these features that you see are there, they're real, they're present, and that they're just a part of HSC processing that we have to live with and mask. The pixel masks do a pretty good job of highlighting, a lot of these ghoulies and masking them so they wouldn't creep into your science if you just kind of downloaded this image and played with it. So hopefully that should get you most of the way to where you need to be for science.
So this is sort of a general question or comment on how we might use results from lower resolution, wider field data to create a model of the astrophysical background at low resolution, which you can then subtract from the higher resolution LSST images, and what you have left is the instrumental background that you want to subtract. So is there any thinking about how we might do that, possibly even using space-based wide field data to model the astrophysical background at low resolution, subtract it off, and thereby get a really accurate measurement of the instrumental background on each image?
Yes, do you want to take that one?
So in Eric's talk, he introduced the background matching idea and how the primary challenge there is producing a reference background to use to match to. And the one place that we have considered using data from other surveys is to construct that reference background to match to. For instrumental, we may be using different language when we refer to instrumental backgrounds, but we have not been considering it for instrumental backgrounds because the instrumental background is so dependent on the detectors and the individual features that result from deficiencies in flat fielding I see background is it's what you do in between flat field. Whatever you don't take care of in your flat fielding, that's your instrumental background that you have to take care of in background estimation. And then anything you can't take care of in background estimation, then the blender has to take care of. So my answer was yes for using as a reference image to match to, but less so for instrumental backgrounds.
Yeah, by instrumental, I misused the term. I really meant everything that's not astrophysical, every background that is not astrophysical.
The question I didn't ask Lee, sorry, Aaron, I'm having a moment, is which background method you're leaning to at the moment that changes on a day-to-day basis?
Well, that's something that I wanted to discuss, hopefully, with Yusra at some point this week, if she's available. We're going to need to use, at least, if we're going to use the novel method, which I do still think is worth looking into some more, we do still have to use at least one of the other ones to do that preliminary sky subtraction. So it'd be a combination of them. But in the end, it just depends on what we can get working in the pipeline in time for, the data previews coming in. So the easiest solution, obviously, would be to just mask. And I think actually we could combine this with Lee's approach of modeling the galaxies. Rather than subtracting them out, we could just mask them based on the Sirsic fits, and then use the other mask for the point sources and stuff, and just sort of combine the two methods. I think that'd be pretty quick to implement. And then if we get that working, we can start looking into the secondary step and see if it actually does improve things enough to merit the extra processing time, is kind of what I'm thinking right now.
Gives me a framework. I've also had a curiosity around whether DM in this process, whether there are limits around how much extra processing time is allowed, is feasible, or extra data created in the process. Like, are there limits on those things, or is that open slather? Like, if you found a solution that created 10 extra files for each image, is that acceptable, or is that highly not okay? Yeah, I was saying, so if you, for every image that you're, like, coad that you're trying to create, you create another 10 acceptable in some higher order framework, or is it perfectly okay?
10 extra coads is because that is a cheaper operation, and so that is within the realm of possibility. If it's a more general question of whether there will be trade-offs that we have to make in which algorithms get run and how much hardware we have, that will be the case. We're not going to be able to run every algorithm that people want, and
that was the message that was the message I think I've been taking away over time, and then was wondering kind of.
Yeah. So for the trade-offs, we're prioritizing algorithms and data products that are lower level and can be used for the higher level pipelines that people are writing. So, for example, if we want to run desks pipelines, we are committed to making it possible for them to run on our PSF models and coad, but we're not committed to running those algorithms during data release processing itself, if that makes sense.
That makes sense. Any other questions? And I will turn and look at the actual camera and talk to, wait a minute, Nishkia had an announcement. Cool. Nishkia, go ahead.
Thanks for giving me some glory, but it's not a big announcement or anything. I just wanted to point out that based on the work that I presented, I have a desk project, and that's in collaboration with the Galaxies Science collaboration as well. And the point of that project is to look at the New Horizons simulations that Garreth presented earlier, because that simulations, because of its high resolution, it has low surface brightness galaxies as well. So the idea is to look at the dark matter content and the dark matter scaling relations of those galaxies in the framework that we've been looking at in the observations in their edges. So if you're interested in participating in that project, or you want to know more details about it, please feel free to ping me on Slack or email me. And if you want to know more about the work, how it could be related to stellar halos and other things that I'm doing, please feel free to write me.
Cool. Thank you. I also, in coming over, notice we have a question from Tom asking, is the only difference for deep coad CalEPS the background, or are there additional calibration adjustments that could be valuable? Lee, is that a good question for you?
Yeah, I think it's been answered on Slack already.
Okay,
Yusra has
cool.
answered it quite nicely. That she,
Yeah.
So I'll refer people to Slack.
Thank you. Oh yeah, I saw that as well. Okay, are there any more questions? Ben.
Hi. So, lovely talk by Nushka. So I noticed something about the scatter with that edge relation. So is that a good definition for when low surface brightness actually start, rather than saying it starts in this band at this surface brightness? We say this is the edge of this. Within here, we talk about galaxies. Outside it, it's the shores. It's the low surface brightness. Is that a good way to think about it?
I think that's an excellent way to think about it, because we are looking at how it is connected to stellar halos. So that's what I showed you with the light survey. And so the edge definition that we're proposing, you can think about it as a limit of star formation. So the edge is tracing the limit of star formation. And so we could think that beyond the edge, you're probing the stellar halo. And stellar halos, I mean, you can have bright stellar halos, right? Stellar halos that are still at SDSS limits. But I think it is one way of thinking about the definition. But I think that what we call low surface brightness in general, it really depends on what kind of data you have. Because, maybe in some data, if you have an object which is close to the limit in depth, then maybe in that data you'd say it's low surface brightness. But in another data set, that low surface brightness object might look brighter, right? So I tend to just think about low surface brightness as being a few percentage of the sky background at that data set. But if you want to think about stellar halos as a low surface brightness object, then you can use our edge definition and say everything beyond the edge is low surface brightness, and let's say extended emission that could be part of the stellar halo for a massive galaxy, for example. Does that make sense?
Yeah, so this is a slightly different definition than your original R1, is that right? I mean, that was just for spirals.
Yes, this is something, I'm glad you're asking me this, because it's something a lot of people get confused about. So in 2020, we fixed the threshold. So we didn't actually look at where the edges are for individual galaxies, okay? We just said, okay, let's use this 1 solar masses parsec squared isophot as a proxy for the overall definition. But the right thing to do is actually to look at where the limit of star formation is. Where is the star formation threshold? Because obviously not all galaxies are going to have the same star formation efficiency, and the threshold might be slightly different. So in this paper, we've actually gone to each individual galaxy and tried to figure out and define where the star formation threshold is. So R1, it is part of the same framework and the same definition, but in the R1 paper, we fixed the threshold. But in this one, we're actually looking at each individual galaxy. Does that make sense? I hope that's clear.
Maybe something to talk about a little later, but the reason that I bring it up is because in H1 there's also a threshold of 1 solar mass per parsec. So that physical, that sort of physical limit, that seems to be the definition for our H1 disk sizes. That's why I thought it was an interesting either coincidence or a good way to sort of intercompare with their results.
Right, so that's a good point too. So the 1 solar masses parsec squared in H1, at least from the Wang et al. Paper that I'm familiar with, that looked and showed that that relationship is extremely tight in H1 size and mass of H1. They actually chose the 1 really kind of by not really with a physical motivation. So they also tested other sizes, but there was not really physical motivation behind choosing it. So we chose R1 because when we were looking in 2020, we chose R1 because the edge was measured for Milky Way-like galaxies at that mass density. So we thought, oh, let's see what happens if we measure the same threshold or the same isophote in other galaxies. So that's why it was fixed. But that was the physical motivation. But now we've looked at it in others. So I am looking at H1 as well. I have not yet looked at into how it compares with our results yet, but thank you so much for asking me that question, and we can definitely talk more about it.
Cool. Thank you.
Yeah,
Okay.
thanks.
Thanks, Nushkia. I think we will call it a day here for this session. Our next session will start in half an hour, and we move room into, I had this before, Tortolita D, maybe A, D, thank you. Okay, good. Unfortunately, that does not have the remote connectivity that this room has, so we'll have to lose and say goodbye to our online attendees, but thank you so much for coming and presenting and questioning for this session. And for the rest of us, we'll continue across the hall in half an hour, and I look forward to seeing you there. Thank you.
Thanks a lot. Thank you. I'm gonna sign off, Lee. I don't know if you hear me, but I think you're the only one. Yeah, because I don't think the room. But I'm.
Great talk, Nushkia. Good to
Oh yeah, thanks. No, yeah, you're by the way very welcome to hear more with the projects. I mean, it's related. We want to see how we can use New Horizon as a predictor because I mean, it would be nice. It would be, I don't know, I've never used hydrodynamic simulations before, and I just think it would be interesting to start with the simulations first, now that we have already done a bit of observational, and then see what kind of predictions you can actually make. And also because, you know, right, especially with the dark matter, people are using the number of globular clusters to estimate the dark matter halos of low surface brightness galaxies. But I want to actually compare those estimators with the simulations, and New Horizon is a great one to start with. I think Sugata always tells me that it's the only one that you can do this kind of comparison with at the moment, because I mean, also because most of the estimates of dark matter for low surface brightness galaxies are for either, you know, very extreme cases or specific classes, but we need something more that's not that's more representative predictions.
I really liked your approach. I had to say, I've had very similar concerns with the half-light radius as well. And it reminded me of some time ago, we looked into instead using the half-mass radius. I guess it's a similar kind of trying to improve some measure of size for these extended sources. I guess you must be all set up with your data set look at that. Would you expect to have any change? You know,
With
with the
half
half
mass.
mass radius? Would that scale
So
well with your measure of the edge?
yes, actually, I think yeah, so. In the 2020 paper, we looked at half mass radius as well.
Right. Okay. So I can go and have a look at that.
Yes, and I mean you do see how different. So in the 2020 paper, we compared R1, so the fixed threshold, to different size measures. So there's the isophoto measures. So we looked at Holmberg radius, as well as R23.5, which apparently produces the tightest scaling relationship for late type galaxies for some strange reason.
Right.
So we used that's in the I band, and Holmberg is in the G band, and half mass. So that comparison is in the 2020, not just 2020 paper. And so this is a sort of more, how do you say, careful. So we actually look at individual galaxies rather than using a fixed threshold. So
Yeah.
then, yeah, looking
Yeah.
at the thresholds, yeah.
Fascinating stuff. Yeah, very fascinating stuff.
Thank you.
Yeah, I'd love to hear more about your upcoming projects.
Yeah, so are you following the Galaxies LSB group and stuff?
I am, but not as closely as I probably should be. But
So
yeah,
I'll
I've
be,
been trying to keep tabs. Yeah.
okay. So I mean, so the project hasn't like started completely yet. I just have the idea. So it is in collaboration with Sugata and Aaron specifically because they're housing the New Horizon and stuff. And so I'll be going to hopefully if I get my visa, I'll be going to the UK in October. And
Oh,
this,
fantastic.
yeah, so we'll start it off, and it is planned to be before the LSST Europe meeting.
Fantastic.
So I
Is that for a
do.
long term? Are you changing position, or is that just for a visit?
No, I'm based in Stockholm at the moment, and I have my postdoc until next year. But it's yeah, so I'm in my last year of postdoc now. But yeah, the project is so it's housed, sorry, so it's sort of hosted by Desk. But then, I mean, I wanted to make it a collaborative one that includes also Galaxy, because it is a topic which both communities are interested in. So yeah. So
Fantastic stuff. Well, good
yeah,
luck with
let's see
all
how
of
it
that. It
goes.
sounds like you've got a lot going on in the next 12 months.
And I do, but that's only the tip of the iceberg, unfortunately, because obviously it's also now job hunting season, right?
That's
So
true.
let's see
That's
how that
true.
goes.
Well, you know what
So
they say. If what's the phrase? If life feels like you're in control, you're simply not going fast enough, or something like that. So,
yeah, no, but also like yeah, I mean I'll just try and see how it goes. But it took a while to write up this Edges paper. Mainly because I mean I moved, so it was work that I did in the last year of my PhD, and then I moved, and then I was fully like trying to figure out postdoc, right?
mhm.
And so only now, and in fact I just resubmitted it a few hours ago.
Fantastic stuff. Wow, productive day.
So let's see. Yeah, I was just like, I don't want to see this anymore. I want it out quickly. So I really hope we got a very constructive report. So I was very happy whoever the referee was. And
Wonderful.
it really helped to improve the work and the manuscript.
That's
So
nice.
I'm excited to share it once it's out. Hopefully the referee doesn't have more comments, and then I can just put it on the archive soon.
Fantastic stuff. Well,
Um,
best of luck with all of that.
yeah, thanks a lot. And I hope to meet you in person at some point. I don't think we ever have.
Well, maybe this time next year for whatever the PCW morphs into. Who knows?
Yeah, let's see how it goes. Anyway, okay, so it's past midnight now, so
All
I'm
right.
going to.
All the best. Take care.
Yeah,
See you next
thank
time.
you so much. Yeah, bye bye.
Bye bye.
Hi. Yeah.
I've actually been subtly trying to find
Hello.
Yes. Testing, testing. Anais, can you hear us?
Yes, can you hear me?
Yes.
Perfect.
Awesome. So I have your slides downloaded on our end just in case, but it's probably just easier to have you share them when it comes time for you to give your talk. Could you practice doing that right now just to make sure everything is fine?
Sure. Give me a second. Can you see
Looks
it?
perfect. Yep. Looks great. And we can hear you.
Perfect.
We're good to go. Okay. And then we will wait until Rick Kessler is online, also remote.
Yes, he had trouble as well finding the link, but I just sent him the link.
Thank you for doing that.
Yeah, there are way too many links that I don't know which one is which one.
Yeah, sorry about that. I might have flooded the chat. I know, I didn't know who would do that, but it looks like I'm the person speaking for everything. It's okay.
I have a question from Rick, which I pretty know the answer, I think. Is there a Zoom link? Because he doesn't have blue jeans.
He says,
Do we have a Zoom link or just tell him to install blue jeans?
if you don't have the Blue Jeans app, you should be able to enter the room through the through your browser.
Yeah, no, I'm gonna tell him to install it.
Yeah.
Thank you for being our tech support.
No worries. From the other side of the world. Very
Yeah,
global.
that's perfect. I'm also surprised Rick doesn't have Blue Jeans.
Back when it used to be the platform desk used, it was only in the browser. They didn't have an app, but it worked in the browser. So,
Say it again? There is in the Slack, but I didn't put it on here. Yeah, sorry about that. I guess maybe it's too late to. I'm going to give like a 1 to 2 minute intro. Correct. Yep. You're going to ask if we need 90 minutes? I mean, the talks are 20, 40, 60, and then we'll see how the discussion goes. If it dies down, I mean, especially because early science is at the same time as this, right? So if we get poor participation, then I'm fine closing a little early.
I see that Rick has joined. Rick, can you hear everyone?
Hello, hello, Rick Kessler. Can you hear us?
We don't hear you.
Can you hear me now?
Yes, we can hear you. Rick, can you try sharing your slides?
I won't be able to do that. In fact, I can't even see a screen right now. It's like making a phone call.
Got it. Okay, well,
Unfortunately, I'm not.
Oh.
Yeah, I'm not at home, and I'm calling from my phone. And I'm calling from my phone. and it's like a regular phone call, so I don't see anything.
Okay.
FaceTime. I don't know how. I've never used Blue Jeans before, so having to learn this 5 minutes before the meeting is a little tight. Is FaceTime here available? I don't think that will work. There's no Zoom, the Zoom option? Using one of our desk Zoom accounts? Hello? Hello, can you hear me? Now I can see slides. That's weird.
Oh, good. Well,
I just hung up the phone and it took me to a screen. Now I can see slides.
okay, great. So I guess the room will share, and you can tell people when to advance the slides. You are also no longer connected twice. Probably related.
Those online, can you hear us okay?
We can hear you now.
I can hear you.
Yes. Great. Okay. Yes, that was a confirmation. It's a little quiet on their end. Is there a way to turn that up?
We can turn up the volume, but if someone's loud, it's really loud.
Can someone remote try speaking again?
Hello,
Yeah,
hello.
this is Deep. Can you hear us?
A little quiet. Yeah, that'd be great. Thanks. Sure. Yeah. And then Rick, can you see the slides now?
I see the friendly reminders, CEO Code
Perfect.
of Conduct and COVID.
That's awesome. Okay, so then I think we should be good to go. I'll just click through your slides for you when it gets to you, and you are the first speaker, okay?
Yep.
Great.
I'll hold my head in one more time.
Great.
After we run around.
Thank you. I appreciate it. Okay. I really don't think we'll need 30 minutes of discussion at the end, so I think we can give people another minute or two to trickle in.
How long is this session?
90 minutes.
If it goes the distance, I have to leave at 6:45. My time, that would be the last 15 minutes.
Okay. All right, it's 3:35, so let's go ahead and get started. Hello, everyone. I'm Alex Galliano. I am co-chairing this session with Alex Maltz, who is remote. And today we're going to be talking about the ELASTIC Challenge. ELASTIC stands for the Extended LSST Astronomical Time Series Classification Challenge. And you're going to be hearing from 3 different people in this session. You're going to be hearing from the LSST AP team on what's going to be contained within the alert packets. You're going to hear from somebody on the simulation side of ELASTIC, hearing about what models we embedded into these simulations and why they're useful, and a little bit of a timeline for the challenge. And then you're going to be hearing from somebody on the broker side on what they're doing right now with the alerts and what they plan to do with them in the future. I just want to mention that this is a really exciting time, of course, for LSST. It's why you're all here, but it's also a really exciting time for this type of infrastructure work. I think the talks in the past couple of days, and if you were at the desk meeting last week in Chicago, I think it was very clear that massive projects like ELASTIC that are testing end-to-end all of the types of analysis that we're trying to do are really central to a lot of our work. So really exciting stuff that you're going to hear about. We're going to have a little bit of time at the very end for open discussion. Let's see. Code of conduct. You all signed it when you registered for this meeting. A couple of reminders are up there. You should look through the code of conduct in detail if you haven't already. Of course, no bullying, harassment, or regression. And let's see, there are a million different ways to ask questions or to give comments. If you're in person, we would prefer if you just speak into the mic, we can run it around. If you're remote, there are a couple of remote participants today, then let's see, we have a Google Doc for notes where you can type in your question. You can type it into the Slack. I guess technically we have the community link, but that's maybe not going to be useful for real-time stuff. So yeah, a little note on. You can also type into the Blue Jeans chat. And Alex Maltz, you should be keeping me honest. I'm going to try to keep an eye on the chat, but I might miss some stuff. So please just shout it out if I missed a question. Sound good?
Yeah, I'll be monitoring the Blue Jeans chat as best I can, and the Slack chat, and also there's a space in the notes document. If you'd like to help take notes, clarify things, if I've misquoted you, then you're welcome to. The document is open. And we'll close it.
Great, thanks very much. And if you're not currently in the Slack, then the channel is listed right there. So feel free to join in on the conversation and add some notes there if you'd like. Okay, so without further ado, let's start off with Rick Kessler, who is going to tell us about the Elastic Challenge, a timeline, the models that are included within it, and why we need it at all.
Okay, I don't see the slides yet.
Yeah, sorry, give me one second. There's not a full screen for this.
Okay, I see like the top half of the slide.
Can you present? Awesome. Can you see this
better.
okay?
Okay. Yep.
Perfect.
Okay.
All right. Oh, I should mention, each of the speakers, you have 15 minutes. I'll do my best to keep an eye on the time. And to be honest, I really don't think that we're going to risk going over, but just to be safe, I'll do that. Okay. So, Rick, whenever you're ready.
Yeah, go ahead. So I'm going to talk about Elastic, the models, and a bit about how the simulation works. So go ahead to the next slide. So just to motivate things, a few years ago, we ran a public 25K Kaggle challenge to photometrically classify 3 million transient light curves in the LSST passbands. So that included 18 models and a magnitude limited training set that was roughly based on the expected performance of Foremost. It was a joint effort between two science collaborations, DESC and TVS. And the primary goal was to motivate machine learning classification, but it was also to improve the simulation infrastructure. And below is just a chart showing the relative fractions of each transient type, which is in Renee's results paper. Next slide. So to the extent of motivating classification, I think we succeeded based on this list or partial list of classifiers that have been used or have been developed using plastic data. I'm not going to go through them. I just wanted to show the big laundry list of classifiers under development using plastic. Next slide. So from plastic 4 years ago, we are now working on Elastic, which is essentially a broker test. And so the goals are to test the alert infrastructure, sending, receiving, processing, all that under the hood stuff. That's really important. We want to test this with reasonably high volume. So it's about 40 million alerts over 3 months. Of course, in practice, 40 million alerts is like a week, but we're going to distribute over 3 months, and to test classification algorithms on transients plus their host correlations. And then in parallel, there's a lot of synergistic development for simulation and analysis going on. Next slide. So I wanted to point out that what this simulation is really for and how it's being used. So that this is an SNANA simulation, and the primary reason for its existence and development is for an SN1A cosmology analysis. And in particular, there are 3 things that we need it for. We do distance bias corrections, training classifiers, and using beams. So roughly speaking, you can think of the simulation as 2 parts. First, there's the physical universe. We want to model type 1A and non-SN1A contamination. Now, of course, contamination to us in a cosmology analysis is always somebody else's gold, so you have to be a little careful about the language. And we want to model host galaxy properties and their associations. Then we want to connect the light coming from these sources to the instrument that's looking at it. So we want to model the host galaxy effects on observations. We want to model cadence and observation properties, noise, and survey selection effects, which we often refer to as a trigger. Next slide. So here's kind of a cartoon of how the simulation works. You can think of it as 3 parts. First, there's an underlying source, an SED source, and then that light from the source travels through the expanding universe, goes through some dust, and eventually goes through a filter in your telescope. Then there's the noise model that says, well, this is what the instrument reports, some flux and ADUs or photoelectrons with some fluctuations. And then finally, on the right, there's some trigger model. And for LSST, for example, it's a single detection. I'll show you a bit more what the trigger model is later. Usually it's 2 detections. LSST is rather bold, triggering on a single detection. We'll see how well that works. Next slide, please. Let's see. There we go. It's worth pointing out some simulation improvements because of plastic and elastic, and I was anticipating improvements, which is why I got involved, even though plastic and elastic are not cosmology analyses. I thought there was a lot of synergistic overlap where everyone would benefit. So, for example, peculiar SN1A are now a standard part of our contamination that we use for training classifiers and using for beams. So it's actually part of our SN1A analysis now. We have transient host associations. You can thank Martine Loken and the organizer of this session for doing an incredible amount of work and effort to make that feasible. We now have PhotoZs. A PhotoZ, I should have said PhotoZ PDF instead of point estimates, thanks to Alex Maltz and company. We also have a light curve library to model galactic transients, something that we didn't have prior to plastic. And AGN are actually a contaminant for SN1A cosmology, so I'm eager for the day when somebody provides a good enough AGN model to actually model that contamination. Also, because of plastic and elastic, the simulation is much more robust to community model input, and it's much more robust to large jobs. So I remember 4 years ago trying to simulate all of wide, fast, deep, and needless to say, it didn't work. But now it's really trivial to generate 30 models in the whole wide, fast, deep overnight on 40 cores. I mean the whole thing, not some pre-scaled subset. Next slide, please. So as far as the models in SNANA, there are different classes of models. I don't mean Python classes, they're like conceptual classes. So the first one is parametric, and SN1A are really for now, basically the only parametric model. It's well defined by its color and stretch. There's something called a non-1A SED, which is an SED time series derived from real data. So if you have 30 or 40 very well measured core collapse light curves plus some spectra, you can kind of splice together an SED model. And Maria Vincenzi has done a lot of recent work improving these models. The next class is called SIM-SED. It's kind of a dumb name, but it's really intended to be a time series from theory models. It can also be from data, but it's more useful for more exotic things like kilonova and TDE or superluminous supernova. And the idea here is you can have the SED time series dependent on things like ejecta mass, lanthanides, and so on. And the original goal of this model, where I was working with the Flash Center at Chicago, was to sort of find the distribution of physical parameters that matched the data. But we weren't able to create enough models. They were just too expensive. So that never really panned out. But maybe someday that can. And of course, many codes can generate theory models, but the nice thing about SNN is it includes all the survey selection effects. So you can start with your underlying theory model and then produce what you would actually observe. And then lastly, as I mentioned before, there's this light curve library for galactic transients, both recurring and non-recurring. All right, I'll pause for questions. Does anyone? I can't see if there's a question, but. Okay, next slide.
Rick, this is Douglas Tucker. Just a quick question. Do you have any kilonova models and if so, from which? And if so, what set of kilonova models do you use?
So in the original plastic, we used the Kaysen 2017 kilonova models, and some more have been added, but that's all I'm going to say.
Other questions?
I think we can add a little bit more detail. So the other set of models are...
Wait.
Oh, is this mic working? Yeah. So the other set of kilonova models are from Bulla et al. And the other thing we've done is you can simulate not just the optical light curve, but we're also simulating LIGO-Virgo-Cagra alerts. So for example, if you were in the DES GW spectroscopic follow-up team, as I know you are, this is a useful test set.
Oh, yeah, good point. I forgot about the sky maps.
Awesome. No other questions in person. Rick, you were smart to go remote. We have a flash flood warning here in Tucson. Do we have any questions in the chat, Alex?
I hope you guys are on a high floor.
No blue jeans questions. Okay, feel free to continue, Rick.
Okay, next slide. So here's a list of all the models. And so on the left are the extragalactic models. They're mostly supernova. And on the right are the galactic models. And of course, the galactic models, there are plenty more, but this is at least the models that were contributed. So on the left, the extragalactic models have pretty good rate models to go with them. And so we expect those to represent, the physical universe. On the right, I think maybe one or two have a decent rate model. The rest, we just made up a number, some reasonable number of events to generate. So don't expect all those to have the physical rate inelastic. And then I've also indicated a lot of contributors, students, graduate students and undergraduates who contributed to these newer elastic models. Okay, next slide. So now I want to move on to some simulations, how the simulation works a little bit. So for simulating the host galaxy, the basic idea is it reads a host lib or host library, which is a catalog of galaxies, either real or theoretical, and their properties. And there's also a weight map, which gives the probability as a function of those properties that the transient resides, in each host. So for example, a supernova core collapse has a much higher probability in a star-forming galaxy than, an old red galaxy. So the weight map would encode that information. And thanks to Alex and Martin, we have weight maps for many, I think most or all of the transients instead of only for a few supernova cases. Next slide. So in the original plastic, the host properties were rather limited. It was, these 3 items. And we knew it wasn't very good and not very realistic, but we just sort of grit our teeth and carried on because you have to start somewhere. Next slide, please. So now we are at a happier place with our host properties. We have a PhotoZ PDF. We have a Sersic profile. So we put transients, on the galaxy according to the profile. It means we can measure a separation. We can also measure what's called a distance light radius and apply matching criteria. And so in this challenge, the number of matches will be mostly 1, but sometimes there will be 0 matches and sometimes there will be 2 matches. That's reality, and the brokers hopefully will figure out how to deal with that. There's also properties, mass, star formation, and color. And these are used under the hood to assign the host based on the transient host correlation. So that's the underlying, physics there. And then there's also a local surface brightness, which we use to anomalously increase the flux scatter. It's something we've observed in both DES and with DC2. And so that effect is in there as well. So basically, nearby, like a kilonova on a bright galaxy, the flux will scatter a bit more than Poisson noise, actually quite a bit more. Next slide, please. So just to show what this flux scatter effect does, this is a plot. And the vertical axis I put in words to the left. It's the actual scatter divided by what you would expect from Poisson noise. And you can see at bright surface brightness, like 20 magnitude per arcsecond squared, the actual scatter is more than double what you'd expect from Poisson noise. And we still haven't quite figured out how to fix that. Okay, next slide. As far as the depth, the plan for now is in year 1 of the challenge, it will be the depth of the galaxies will be based on a 2-week co-added depth. And then in years 2 and 3, it will be based on a 1-year co-added depth. So that will impact the fraction of hostless galaxies. Now, I don't know the real timeline for getting a 1-year co-add or a 6-month co-add. This is just a rather arbitrary. If people really feel strongly that this is woefully wrong and have a better model for the depth versus time, I'm happy to implement that. All the PhotoZs, however, are based on a 1-year depth. It's really a coding practicality. It's a bit more difficult to have the PhotoZ depth varying in the challenge. Okay. For the cadence, it's based on OpSim, but SNN's simulation doesn't read OpSim. There's a translator that translates the cadence. And the idea is we pick 50,000 random sky locations over the wide, fast, deep area. And for each location, we sort of drill through and identify every observation and record the image properties, essentially, which are listed in brown. And then using the model magnitude at each MJD, the sim computes the observed flux and the uncertainty. Now, of course, with 50,000 locations, we're generating over 100 million events. There would be a lot of duplicate RA and DEC locations. So we shift the coordinates to a random location within a small radius so that you don't get duplicate RA DEC locations. There's no large-scale structure, so don't try to look for that. And the selected host from the host library is just moved to this random location. So the galaxies are representative, but we don't literally use their coordinates. Okay, next slide. So redshift, we select the CMB frame redshift from an appropriate model. We transform to heliocentric, and we pick a random peculiar velocity. Again, no bulk flow correction, so studies of sigma 8 and things like that won't work here. Next slide. For the noise model, it's in the circled with the orange line. So there's a source, the source itself contributes some noise, but most of the noise typically is from the background sky, which is B times the noise equivalent area. There's also a Poisson noise from the host. And then this S_sim, that's the anomalous noise from bright galaxies. It's empirically observed. We don't really quite understand why it's there. And this comes from DC2, studying DC2. Next slide. So this is the trigger model. It's a single detection, and it's based on how DIA performed with DC2. So this is the efficiency for detecting as a function of signal to noise. And a good way to characterize it is at 50% efficiency, the signal to noise is 5.8. But it's not an exact step, it's a curve. Okay, next slide. See, I was asked to show what is in the training sample and alerts, so it's a bit detailed to discuss here, but there is a website that has that detailed information about exactly what is there and the variable names. Next slide. Okay, the schedule. So the training sample, which is really only to train classifiers, was released back in May, and there's been a few updates with bug fixes, so thank you everyone who noticed and reported those bugs. It's FITS format, it's publicly available, but it's there just to train classifiers. It's not to grease the wheels of the brokers. For the brokers, we have a 10% alert sample. It's an Avro format, and it's being restreamed to the brokers every 2 weeks, starting from mid-June, and will continue through mid-September. And Rob can give you more details about that. But the idea is that the broker teams can keep debugging their infrastructure, and if they're on vacation, they can come back later and debug it. We also did a full 100% test generation in late July to make sure we could do it. We generated the full SIM, translated everything to alerts, and loaded the TOM database. So this stuff in green was really all just sort of debugging and getting ready for the challenge. So the idea is in mid-September, we plan to start streaming the full 100% sample. And that will continue essentially until Christmas, mid-December this year. There will be a little over 4 million events and more than 40 million alerts streamed over that time. It's about 90 gigabytes compressed, so it will be several hundred gigabytes uncompressed. And depending on how things go, we might restream again in the winter of next year if people feel like they didn't have things debugged well enough and they want another chance. And that's all I have.
Great. Thanks, Rick. Could we maybe get one question if we have it, and then we'll save the rest for the discussion at the very end, if there are more. Okay, Alex, any in the chat?
No online questions yet. If you have
Great.
any, please put them in the document. We'll get to them.
Awesome. Okay, so moving right along, thanks, Rick, again. We heard a little bit about what it was like to simulate alerts. Now we're going to hear a little bit about what it's like to generate real ones from Melissa Graham.
Okay. Yeah, so Alex and Alex suggested I could come and tell you a little bit about the data products for time domain astronomy, and in particular, exactly what's going to be in the alert packet. So my name is Melissa Graham, and I work for the data management team as a science analyst. So that's the context for me being here and telling you about what's in the alerts. But let's take it back a step and kind of just talk about all of the LSST data products in general to have some context for the alerts. So as you may have learned yesterday, if you were in the intro to Rubin session, or as many of you already know, as the raw data comes off the telescope, one image every 30 seconds, it gets processed by our prompt processing pipeline, also known as alert production or the AP pipeline. And what happens to it, it first undergoes instrument signature removal, so the standard standard reduction and calibration. And then it undergoes difference image analysis. The short form is DIA, and that's where you subtract a template image that was made from images obtained, say, the year before. You subtract it from the new image to make a difference image. Then you run source detection, characterization, and measurement on that difference image. So you have a bunch of sources you've detected in the difference image. We call them DIA sources, difference image analysis sources. And every one of those that we detect with a signal-to-noise ratio greater than 5 triggers an alert. An alert is it's basically just a little ASCII file or packet, we'll call it, and it's just full of all the information that LSST knows about that thing that it just measured. So it knows like coordinates, flux, that kind of thing. Those packets of the alerts go to what we call community alert brokers. Those are sort of independent software systems that are being developed specifically to deal with this flow of alerts, flow of these millions of alerts per night, to sort through them, filter them, and make them available for users who want to do real-time science. So as someone interested in doing science in real time with Rubin Observatory, it's really the brokers that you're going to be interacting with to use the alerts that are made. And those are things like Antares and Alerce and other brokers. I don't really have slides about the brokers. But that's what an alert is. That's how it gets made. There are other kinds of prompt products that Rubin Observatory will make as well. So, and within 24 hours, basically, what we call the prompt products database gets updated with all of the detections from the night before. So that's the same data that has gone out in alerts, but it's in catalog format. So you could log in to the Rubin Science platform, for example, and whatever cadence suits your science schedule, daily, weekly, monthly, whatever, and you can be querying those data products in the prompt products database to see, if you can find anything that's risen by X magnitudes over X days in your favorite filter, whatever the thing is that you're interested in finding. So you can also query the prompt products database that way. The other time scale that we sort of work on, so there's the prompt data products, 60 seconds, 24 hours, but then there's also the yearly data releases. Every year, all of the data that was ever taken by Rubin Observatory gets reprocessed, so that every image is re-reduced. All of the difference image analysis is redone. So even at year 6, you're redoing all of it with the latest versions of the LSST Science Pipelines. And you're also restacking all of the data to make very deep coads, and all of that comes out on a yearly basis. So if your interest in transient-related science is more like rates, occurrence rates, population studies, that kind of thing, you're not necessarily needing to use the alerts. In that case, you might actually be more interested in using the annual data products that also have the DIA in them to go through, find your giant populations of things, and do it that way. So that's kind of a broad overview of all the different types of LSST data products for transient science, and that's how alerts fits in. The other way that alerts are different is that they are a world public data product. Everything else that Rubin Observatory creates has a 2-year proprietary period, and also the Rubin Science platform is proprietary to data rights holders, which is everyone working in the US and Chile and named members of international teams. So it's still like 7,000 to 10,000 astronomers worldwide, but still there is that threshold of being a data rights holders, whereas the alerts are world public. they can be shared anywhere with anyone. So that's some context for alerts. So I wanted to just pick out now, even in a little more finer detail, data products that are useful for time domain astronomy. So, and really give you some of the nomenclature as well. So we have processed visit images, also called PVIs, also called direct images or single visit image. I haven't got them fast. Yeah, so we have lots of names. They're also called CALEX. So there's so many names for these. It's just the single visit that was obtained of a single area of sky at a time in a filter. So those are the PVIs. Then we have the difference images that we just talked about, the template images, and the deeply co-added images. So the first three are sort of obvious how they relate to time domain data products. But I've included those deeply co-added images in this list because that's where you get the host galaxy and the populations from, so the context for your transient of interest. So those are the image data products that we would expect you to be using for transient science. Then there's the catalog data products, which I just spoke of too, the DIA source. Then there's also DIA object, where you have the source, which is add detection in a difference image at a certain time in a certain filter. But the DIA objects are associations of DIA sources. So that's at a certain location of sky where you've seen multiple DIA sources appear. We collect those together and they're stored as a DIA object. And then there's additional measurements and characterization of the object that have to do with the light curve. So you have some sort of easy to measure light curve parameters for that DIA object, like the peak observed brightness or peak observed flux. That's a really obvious one. And some other things about like amplitude of the light curve, things that are easy to measure are all in the DIA object. There will also be a DIA forced source catalog where forced photometry is done on the difference image at the location of every DIA object. So you might have a variable where only sometimes it becomes a DIA source, because only sometimes we can detect it at signal to noise ratio greater than 5. But you want forced photometry when it goes below that. So in that case, you're using the DIA forced source catalog. The fourth catalog that I've included here as relevant for transient science is the object catalog, because those are the detections on the deeply co-added images. So that's where you're getting your host galaxy brightness, size, color, shape, all that kind of stuff is coming from the object catalog. And then, of course, down at the bottom here, I have the alerts, which is the data product we just talked about as relevant for time domain astronomy. So I want to dig just a little bit deeper into what exactly, like what are the measurements in the alert that you will have access to. So within that DIA source record, and that's the thing that triggered the alert to happen in the first place, you get things like a unique identifier, which filter it was, which program that image was obtained under, whether it was wide, fast, deep, or deep drilling field, basically, or a TOO. That should be in there as well. You get the mid-exposure time, the time at mid-exposure, a centroid, so the coordinates, calibrated fluxes of a variety of types, so PSF, aperture, etc. You have some shape measurements, like whether it's trail or dipole. If you were in the DIA session earlier, there's that kind of information. The signal to noise ratio, and then, of course, a spuriousness parameter, which is like a real bogus parameter that helps you make cuts on things. And also that will be provided will be like what spuriousness cut you should apply if you want a completeness of X or a purity of X in your sample. So that kind of characterization of the real bogus should be done for you as well, so that you can make cuts not just on flux, but also on the real bogus / spuriousness parameter. Also within the alert packet, of course, you have the DIA source, which triggered it, the DIA object that it was associated with, and all of the DIA sources that are associated with that DIA object, which is just the complicated way to say you have the light curve, basically. So you have like a 12-month history of everything at that location in the sky as well. And what else did I want to tell you? Yeah, so that alert record also includes if there's a history of forced sources. So if we saw it and then it went below detection threshold and then it came back, those forced sources are also included in the alert. So it's in that history. And right, so there's the situation where you have no history. It's a completely new DIA source. Nothing has ever been detected at that location before. It becomes its own DIA object. Essentially, it's a single source DIA object. But it's very important for transient science to know what the limiting magnitudes recently were in that area. And so it's a little bit too time consuming to go back, and within that 60 seconds, we can't go do force photometry over the last 30 days. But what we can have ready is the limiting magnitude of any images that overlapped at that area. So that's what you get as your like recent limits in an alert for a new source. And then within 24 hours, we can go back and do that forced photometry for the last 30 days. And then, so if you have one night, it's a new DIA source, it goes out as an alert, and you get the limiting magnitudes from the past 30 days. If you see it again sort of the next night, then that new alert that comes out for that same DIA object, now you have the 30 days of forced photometry as well. So that's how we're getting you the forced photometry. Pre-covery is also the word used there. That's how you will have access to that as fast as possible. And then, of course, in the alerts, the last thing on the list there is the image stamps. So it's the difference image and the template are what you get, because you can reconstruct the direct image from those two things. And for each of the images, it's flux variance and a mask plane. And the size of those stamps they're never smaller than 30 by 30 pixels, which I think is like 6 by 6 arc seconds. But if it happens to be, if the footprint happens to be longer, so for example, like trailed sources, then I think the stamp is going to be larger as well. You want to like have the stamp at least be the size of the footprint. So that's what's in the alert packet contents. From here, I go into a bunch of FAQs. So may I pause for questions now? Just because that was a lot of info. So I'm happy to take questions before continuing.
Charles Liu has a question in Google Doc. Would you like to ask your question?
Sorry, who?
Charles Liu.
Yeah. Can I be heard?
Yes.
Yeah. Hi. Just wanted to confirm that the 24-hour cycle and the 1-year cycle products are independent of the 60-second alerts, right? If we're not quite down to 60 seconds in 2024, the stuff will still come out every day. Is that right?
Yes, if we don't get the AP production down to 60 seconds, everything else I think stays the same. It's just it'll be 120 seconds or wherever it lands.
Okay.
Yeah.
I figured that was the case, but I just thought I would confirm that there's no coupling of the different time scales. Thank you.
I don't think so. And I don't think, as far as I know, it's not on the table to cut any of this to get down to 60 seconds either, because most of what we're putting in the alert we pretty much figure is essential. So I'm not sure if that was your question, but I don't think that's on the table.
Yes, that's exactly the, yes, thank you so much.
Okay. Yeah, come up and. They'll hear you online.
Okay.
Yeah.
So I was curious whether does this work? Okay.
You won't hear, but they hear you. Yeah.
I was curious whether there's any idea to have a force photometry service that would go longer, like that you could request and retrieve the force photometry. Thanks.
Yeah. So for force photometry, for anything that's been detected, you can leave it on because there's more questions. Yeah. For anything that's been detected, we'll continue to do force photometry. I think it's for 12 months. That we continue to do that force photometry. Alerts don't come out if the thing has faded below signal to noise ratio of 5, but the force photometry will continue. So you can query the prompt products database to get that force photometry for your object. And then, does that answer your question fully? Or is your question more about can users, okay, I'll extend your question. So there's also the science use case where some people want us to do force photometry always at these locations on the sky, whether or not we detect something. And that's definitely on the table. And right now we're figuring out the process for making that list of coordinates. Yeah.
I think it was like more.
Yeah.
I think it was also like a force photometry request service, so an API where one could submit an array and deck and then get force photometry on demand at that location. And I don't know if that's doable or through the RSP or how you might do that.
Yeah, that's absolutely doable through the Rubin Science platform. So you would log in, you'd probably be logging in, I think now, if you log into the notebook aspect and you would use the LSST Science Pipelines force photometry, you'd give it your own coordinates and it could do it for you. That's how it is now. Whether we could do that through API, I'm actually not sure at this point, but some capability will exist for, yeah, absolutely.
Nevin, did you have a question?
If you don't mind, you can pick it up too and hold it, or, yeah.
Sit here.
Okay.
I just want to make sure I understand the alert packet contents. So a DIA object can contain multiple DIA sources, and a DIA source might be a supernova, and a DIA object, for example, could be a host galaxy.
Not quite. Not quite. So a DIA source would be a detection of the supernova. The DIA object would be all of the detections of the supernova.
Oh, okay.
Yeah, so object is like that point on the sky, and then the source is all the individual detections. So you could think of it as points on the light curve. Yeah.
Got it. Thank you.
And then the object is the host galaxy.
Without DIA in front of it.
Without DIA in front of it.
Okay.
Yeah. Yes. Clear as mud. Yes.
It makes sense now. Thank you.
Okay. Don't humor me. You can say if it doesn't make sense.
It does.
Okay. Yeah. Come on.
So for the DIA forced source, would we compute the same time series features for the DIA object as well, or would those be separate?
So for time series features, that will be calculated and go in the DIA object. Oh, I'm assuming they're going to use DIA forced source because you want to use all the
For
information.
variable stars, I think it would be very useful. But
Yeah.
will there be an overlap in the computation, or is it going to be mostly or mainly the force source?
That's a question I can't quite answer yet. I think mostly we want to use force source wherever possible. That's the one you want to be using because it's got more information. What I also didn't mention is the DIA object and the DIA source as well. It has not just the difference image flux, but also the direct image flux. So for variable sources, that's even more what you want.
Right.
It's the direct image flux over time. So, so exactly what time series features this is actually an FAQ, is not determined yet, but some of them should be using direct image fluxes instead of difference image fluxes for variable stars. Yeah.
Cool. Thank you.
Yes, it's a good question. Thanks. Douglas. And then it's the bottom one. Yeah. Press and hold. You'll get it. You really have to just be like, I want.
Oh, magic touch. What was my question? How do you use about no? Is there are there any variations of these alerts available for DP 0.1 or 0.2?
No, not yet. No alerts got made, but I feel like I saw alerts from DC2 go by in someone's talk.
We have some simulated alerts from DC2 light curves.
Oh, sorry. Yep.
We do have some simulated alerts from DC2 light curves, but a much more useful data set is just Elastic itself, which has all of the alerts streaming to you with the right format for the most part.
Yeah.
Okay, thanks.
Yeah. Here, you can use this one.
I was wondering if you could say, and it's maybe a little bit into the weeds, a little bit more about this limiting magnitude calculation you were saying. Is that, per whole object, how is this done per band, I presume?
Yeah, the signal to noise ratio greater than 5 in a band, and that's the detection influx in the difference image. Yeah, exactly. Yeah. Okay, any more data products related questions.
Can I add a comment and a question? So on your next slide, you had features in that we haven't included them in Elastic because we don't know how to compute them. There's no information, for example, on when LOMS cargo features are computed, after how many detections, etc. So that's missing. But do we have any more guidance on when those decisions on features will be made?
I'm just thinking, I don't know when we're going to decide on that. I know, hold on. Yeah, second FAQ there about derived variability parameters. It's ls.sc/data management tech note 118 is sort of the current thinking of everything we could do. Yeah. So that's actually a question for Eric because he's leading that, and I'm not sure what our time scale is. Yeah.
The other thing that you might be super interested in is we added in some features that you don't have in the alerts, in particular photo Z PDFs. And a lot of brokers and classifier teams here will almost certainly want that information. But that is not in the DPDD anywhere as a thing that's going to be provided by LSST. And even if CMNN is loved, that's good enough, I think.
Okay. Yeah. So it won't be in the alerts. Photo Zs don't go in the alert packet. So we'll just jump around our FAQs. So, right. The photometric redshift goes in the object catalog, which is proprietary. So we can't put the photo Z in the alert packet. But what will go in the alert packet is some host association. So let me first draw your attention to the first FAQ about host association. So within the alert packet, we'll give you, so host association gets done as part of that 60 seconds. What goes in the alert packet are the LSST object IDs for the 3 nearest stars, the 3 nearest galaxies, just by on-sky distance. Also, the 3 nearest extended objects in a separation distance that takes into account the size of that extended object. It's kind of like still to be determined exactly which association code we use to do that, that distance. And then also the nearest low redshift galaxy. So we'll have a list of low redshift galaxies, and they'll just always have the nearest one in it, just in case it's like a low redshift transient. So with the object IDs for those nearby things, you can then query the object table and get the photo Zs. And they will have, the photo Z data products do include like point estimate and uncertainty, but also the full posteriors. And so brokers are really anyone, any data rights holder is free to use those photo Zs. So that's how we're expecting brokers to use this host association data, get the photo Z data, and use it.
I'll just point out that that means 7 separate calls from different brokers to the same database to all retrieve the same pieces of information, when it could go just the one time in even a proprietary little packet in a topic that only the brokers knew about.
Interesting.
It's a simpler solution in many ways.
Yeah, actually, this is the first time I'm hearing of like a proprietary packet.
Just create a topic name that only the brokers know about.
Have you brought this up with me? Okay.
Hi, my name is Garreth Martin. Give me a chat.
Yeah. So this is an idea I haven't heard yet. And this is also something I'm not super clear exactly how hard this is for brokers. If it's quite hard, we don't want to impede science. Okay, let's talk further about trying to solve this issue because I haven't pushed too hard on it yet. Yeah. Okay. So we've covered host association. We've covered that you'll have the object IDs and you can retrieve host galaxy data. We covered photo Zs. Should I continue with my FAQs?
It'd be great if you could real quickly say postage stamps, but before you do that, Alex Maltz, is there a question?
There's a question from Natasha Abrams in the Google Doc. Please ask your question if you can. Read it.
Sure. I think this might be in the FAQ as she's been flipping by, but I just wanted to know how many nights of data will be able to access at one time that are associated with an alert. Right. I guess the alert itself is only one data point, right? But how many nights?
Yep. So the alert itself gets triggered on one data point, but you'll always get a 12-month history.
Well, I see. And then in the yearly releases, we will be able to access all the entire data set associated with that data point?
Exactly. Yep. The annual release, you'll have the full, however many years we are into the survey, you have that many years of a light curve.
Okay, thank you.
Okay.
And then Alex, are there any more in the chat?
Not that I see at the moment. Oh, Tom Laredo has a question just now.
So Tom, if you're able, feel free to unmute and ask your question.
If not, I will read it out loud. Regarding including object IDs, will those be available before DR1? Are they produced as the survey goes for the 24-hour data? Will photoses be available for those before DR1?
No, those can't be available before DR1 because we need that object catalog. Yeah, it's a good question.
Okay, if there are no more questions for now, feel free to continue on with.
Okay, I'm going to go straight to the question FAQ you requested, which was, would brokers be able to retrieve a larger postage stamp because that 30 by 30 pixels doesn't get you the full host galaxy? And the answer to that is yes, you can retrieve them. For example, from the Deep CoAD from the most recent data release, that's probably the easiest thing to use. There will be an image cutout service. There's a prototype of that ready actually now even that we're using, well, starting to use with DP0. I haven't actually touched it yet and started to see what it's like, but it does exist. And that's for data rights holders, right? Because it's the 2-year proprietary period. That image cutout service, as far as I don't know what the maximum is going to be on that, but about the size of a patch or like at least a single CCD. So data rights holders can get those larger stamps of the science and difference images, of the science and difference images, the direct or difference images once they become available during the prompt time, which we heard earlier today. I think Bob said that's currently at 80 hours. Who was in the multi-messenger? Yeah, it was 80, right, that he said right now? Yeah. And I'll actually just stop there and just take more questions if there are any.
Oh, I had a question, although I'm not sure how to raise my hand.
We can hear you, so go ahead.
When there's a detection, are there any cuts that are made to throw it out, like cosmic rays or artifact near a diffraction spike? Or do you just put a flag on it and pass everything through regardless?
Yeah, no, there's definitely something happens there. So there's the signal to noise ratio of 5 is 1, but then things that are like we can characterize as artifacts don't go in the alert stream. So that's things like cosmic rays. What I don't remember is exactly how it gets done. Maybe that's still in development, but we definitely aren't going to be passing out things we know are junk, basically. Yeah.
Then there was one more question here in person.
Yes. So the brokers only deliver to people who have data rights, or okay.
No, so the alerts go to the brokers, to the 7 sort of selected brokers, and then they are free to have users from wherever because the alerts themselves are world public.
Okay.
So it's up to the brokers to have their own users. Yeah.
Okay.
So the question you asked got earlier about host galaxy identifiers during the first year of operations is a little worrying. So is there no host information at all? in the first year? Because you must be assigning identifiers anyway for objects.
So, right. So I think the early science session is happening now. And so there will be some sort of incremental template built as we go. And I think there will be, it makes sense to have incremental object catalog also as we go, but I'm not the one who can sort of promise it. So we should just follow up and make sure that that's, but even if that does, I still don't think there'll be photo-sees.
Yeah, no, I think that's fine in year one of operations, but longer term, this will be a sticky issue.
Yeah, but an incremental object catalog sounds doable to me, but we should check with our early science people, with Leanne, basically, yeah.
All right,
okay.
We want to save a little bit of time for brokers, so let's give Melissa a round of applause again. All right, and next, okay, so obviously a big infrastructure pipeline. We start off with our kind of underlying SCP model of transient host galaxy. Rick talked about that. Then we pipe them into alerts using, to the best of our ability, the information provided from LSST AP about what's going to be available in alerts. And then all that information goes out into broker systems that are tasked with processing this data deluge and doing meaningful science with it. So to hear a little bit about how that gets done, Anais Moeller is going to talk about the Think broker and its science goals. So whenever you're ready, let me stop sharing. Yep. All right, feel free to share screen, Anais.
Perfect. Hopefully this works. Can you see my slides?
Yep.
Excellent. Hello, everybody. My name is Anais Moeller. I work with Think. And today I'm going to tell you a little bit of the Elastic Challenge seen from the broker side. Before I start, I would like to acknowledge the traditional owners of the land where I work. I actually am in Australia, so I acknowledge the Wurundjeri people of the Kulin Nation. And I'm going to talk a little bit about the work we have been doing in Think. So this is not only myself, but a team of people trying to tackle the Elastic Challenge. So for us, from the broker side, we have two main challenges. There is the infrastructure challenge, which is basically connecting all these alerts that we're going to receive, receiving them and sending them back, enriched, selected, etc., a little bit to mimic what will happen with Rubin and to test the data volumes, the latency, etc. The Elastic team has to split it in two phases. So we are right now in phase 1, and we will be in phase 2 later in the year. The second challenge that we see, and I'm going to discuss a little bit about some preliminary stuff we have been working on, is classification. So when we talk about classification, this can be a complicated term, I think, because some people think it's just machine learning scores or a probability of this object being that, and other people think it's basically a filter sample, which are two things that could be the same, but are not necessarily the same. So I think I'm going to tell you a little bit about those differences as well, because I think it's very important that we start thinking about them. Now, of course, the brokers, we are not just one. This is the list of full stream brokers selected by the Rubin project. These include people that are right now in the room with you and online. I'm going to tell you the perspective from Think, because that's where I work. That doesn't mean that the other brokers are not doing amazing jobs and doing different things with Elastic. Now, what is Think? Think is not an acronym, which is incredible, I know. It's a community-driven effort, so we want to touch as many science cases as we can. So it's open to everyone. As we heard from the questions in the previous talk, brokers will receive public data and will transmit that public data to the world. So we are as transparent as we can. So we have open source code, etc., and you can get the data publicly without being part of Rubin. Now, of course, having data rights gives you other benefits that we have heard from Melissa's products, slides on products, but the idea is that the broker can touch any community that is interested. We're a team of around 40 researchers and engineers, around 7 countries and growing. And on the top right, I put actually a picture of our first collaboration meeting, which we finally did this year due to COVID and other things that have happened. We designed Think for Rubin. So from the start, we have been working with big data technology like distributed computation. And since 2019, we're processing CTF2 data, just the public part. So that's already available in our webpage. Below, I put a link to the paper with our first publication. If you have questions about the architecture of Think and science cases, I'm not going to get into that exactly. We have a lot of science cases that I'm not going to talk at all today. So if I don't mention your science case, that doesn't mean that the broker is not doing or cannot do it. So I will summarize what we do as enrich, select, and distribute to maximize science. And when we talk about these things, I'm going to start a little bit in the other way around. I'm going to start with distribute, because how do you distribute? Let's say you get the CTF or Rubin data. We enrich it, we select it, we do all this magic in the brokers, and we distribute them. So there are 2 ways that the brokers can distribute data. One of them, it's to trigger follow-up, like, for example, a real-time API. That's what we have. It can be a Kafka stream. It can be like a Slack bot. It can be whatever you want that is automatically triggering a follow-up or a reaction. But it can also be a little bit like a human-based thing, like a web portal or a REST API, so you can query the database and do your science analysis from home, from your computer, or at work. So this is how it's structured for the production mode, which is using data from the surveys. For Elastic, it's a little bit different in the sense that we're testing the infrastructure, the part 1. We are getting this 10% of the sample that was previously mentioned in the brokers, like in a loop. And we process it, we ingest it, and then we return it back. So what we have been doing is, we are receiving this 10% of the sample. We have adapted Think for LSST filters, the fields of the alerts, because they're a little bit different from, for example, CTF. So these are little infrastructure details, but they're important to tackle. And we have also resent the stream back with fake classifications. If you can see on the right, this is an example of what we sent back at one point. You can see that we have alert ID, when we ingested the alert, what version are we running, and you can see the classifications, and you can see the classifier params that is coucou. Coucou is in French, hello. So that tells you that our infrastructure engineer is French. So we have a little bit of French in our parameters back. But this means that it's right now just a dummy classification. We're not sending true classifications back. And I think this is the next step of the Elastic Challenge. And I think it's a very interesting sample to work on to see what we can do with Rubin. Now, with the Elastic Challenge, and in particular the simulations that Rick told us a little bit before about, we want to see how we can enrich them and select them. In real life, what happens is that we get that data from a survey. We first do a real bogus quality cuts, basically, and the information that Melissa was telling us just before in the talk. And then we start enriching it with information from things like catalogs, like cross-matching coordinates, trying to cross-match footprints, using like VOE events, GCN notices, for very fast transients, maybe like a gravitational wave detection, maybe a GRB detection. And we also compute like features. Let's say that you have a light curve. Is it rising? Is it fading away? Is it red? Is it blue, etc.? This is how we do it in real life, that together with machine learning classifiers to provide scores of these objects being potentially a supernova or potentially a microlensing event. Now, we have a big machine learning background. In particular, I like you can see that we have different algorithms going from supernova classification to microlensing, fast transients, and we are now implementing some new ones, which uses multiclass. I think one of the things I would love to discuss is the difference between just thinking of the machine learning classifiers providing this score and actually selecting a sample. What we do is that we get this information, and then people can select what is their threshold for scores, plus cuts, for example, with cross-match of catalogs and other information. Is it red? Is it rising? And then you can get like a filter stream and get your information of the candidates that you're actually searching for. In Elastic, we don't have this. So there is some contextual information, which is very valuable. But I think this is something that we need to think about when we move to Rubin. Elastic is super important to understand how machine learning classifiers are working, how our infrastructure is working. But as we move forward, we also need to think about the bigger picture as well. Now, we got the training set for the classifiers, which Rick mentioned before. On the right, I'm putting the taxonomy of the classes that we have. There are some big taxonomies like supernova, like fast, long, recurring, and then you have the little classes below. I think it's important to know that from the broker side, this taxonomy will impact the classification performances. In the sense, some classifiers are more targeted to one type of object than other, or maybe a broader class or a smaller class. So from the broker side, this is important to notice. Also, the size and balance of the subclasses can affect the potential performance of machine learning algorithms. I'm not talking here whether you can do data augmentation or not. It's, let's take just the raw training data and train our algorithms. Can we perform competitively? Because it's well known that some algorithms will perform better with very large data sets because they don't get feature extraction like recurrent neural networks. But if you get a random forest with a feature extraction like a fit over the light curve, then you can get better performances with a smaller training set. So you need to balance all that when you're working with a broker. The other thing that we have been, and I will mention this a little bit more, is baselines. What do I mean by baselines? This is the history. So we know that we will get this history in the alerts of 1 year before the object was detected, and the 30 days that were mentioned for the first photometry, the second detection. But when we get a training set, we get like basically the full span. So do you use the whole thing to train because maybe you don't have all this information? Do you make cuts, etc.? And this is linked to what I put below, which is magnitude limits and detections. Now, this is a lot of words. I think the next thing is more interesting, is just an example of some of the likers. These are likers that we plotted different ways, so don't worry the different styles. From the Elastic training set. And you can see we have some very nice type 1a supernova, we have some stars, but then you have type 1a supernova that basically have 5 epochs with huge gaps in between. SN1BC, and you can see here on the top right, I don't know if you can see my mouse, but I plotted like a line where it's the peak supposed to be of that 1BC. And you can see, well, this is potentially a supernova, but then you have all this potential noise or something else down here, which is a good question. Do we use that to train? Is it just like noise? And this is something that we need to think in the real life. We have a lot of noise. Can we mimic it? How big are the likers that we need to use? So I am now going to go through some of the machine learning tests that we have been doing for Elastic with Think. This is all very, very preliminary. So whatever I tell you is not necessarily the end game, but to give you an idea of what type of algorithms are we using, what challenges do we have, etc. So this is a classifier that we have right now in production with CTF that is finding early type 1a supernova with active learning. So the idea is the following. We want to find rising events, basically. So we want to find things that are rising, that look like type 1a supernova. We do some type of filter extraction that you can see here on the left for each filter observations, we actually fit a sigmoid and try to see if this object is rising. We make a cut to only get this rising object. One of the challenges we have found when we were dealing with the training set is that some of the events were way too faint. And that was producing a problem with the sigmoid fit. So we had to raise a little bit the bar of the signal to noise. So this is something that is important to know. Like some algorithms are not tasked for very, very faint things. So we had to put that at least one filter had a flux cal, which is it's a flux normal that comes with a 0 point of 27.5, if I recall correctly, bigger than 100. So this is one of the limitations right now of these plots that I'm showing you. We're trying to see what we can do to improve it. But to tell you a little bit about the active learning idea is the following. We know that we don't have complete training sets of supernova and other types of transients and variables. So what we do is we get a machine learning classifier in a loop, basically selecting the objects that we would like to have a tag or have a spectroscopic follow-up, and you train it that way, improving every time your classifier. So right now, because it's all simulations, this is not real life. But you can do this thinking that we can trigger follow-up with like Formos or any other telescope. So this is an example a little bit of how fast the training goes. We're talking about 60 loops here. And you get, actually in blue is the active learning loop, in orange is the randomly